Thermogravimetric analysis is a type of thermoanalytical method. Thermoanalytical methods involve those techniques such as thermogravimetric analysis, differential thermal analysis, and thermometric titrations. Another technique which has been developed is known as fractional thermogravimetric analysis. These techniques involve the measurement of weight loss due to the escape of all volatile matters from a sample during heating. Thermogravimetry is a technique in which a change in the weight of a substance is recorded as a function of temperature or time. In differential thermal analysis, changes in heat content as a function of the difference in temperature between the sample and an inert reference compound is measured. In thermometric titrations, changes in solution temperature are measured and plotted against the volume of titrant. Thermal analysis incorporates all those techniques in which some property of the system is determined as a function of the temperature. In thermal methods, the thermal behavior of a substance is recorded as a function of temperature and or time, and the recorded curves are considered as thermal spectra or thermograms. Thermogravimetric analysis and differential thermal analysis are valuable techniques because their applications do not impose any restrictions on the systems being studied. The technique of thermogravimetric analysis involves the weighing of the substance under investigation while it is being heated at a predetermined and preferably linear rate. An accepted definition of thermogravimetric analysis is as follows. Thermogravimetric analysis is a technique whereby the weight of a substance in an environment heated or cooled at a controlled rate is recorded as a function of time or temperature. There are three types of thermogravimetric analysis: isothermal or static thermogravimetry. In this technique, the sample weight is recorded as a function of time at a constant temperature. The second is the quasi-static thermogravimetric analysis, where the sample is heated to constant weight at each step in a series of increasing temperatures. The third type is the dynamic thermogravimetry, in which the sample is heated at a uniform rate, but the results are subjected to errors due to the effect of changing air buoyancy and convection. The measurement of temperature, heating rate, and heat of reaction are overlooked. This technique, that is dynamic thermogravimetry, is suitable for the determination of approximate quantitative thermal behavior of a system, but it cannot be used for determination of precise constants. A typical thermogravimetric curve is shown in the figure, which represents a curve for copper sulfate pentahydrate. The main important features of the curve are the horizontal portions, which are also known as plateaus. They indicate the regions where there is no weight change. The curved portions of the curve indicate the regions where weight loss occurs. The thermogravimetric curve is quantitative in nature, therefore calculations on compound stoichiometry can be made at any given temperature. Thermogravimetric curve also helps us to determine the procedural decomposition temperature, which is the lowest temperature at which the cumulative mass change reaches a magnitude that the thermobalance can detect. Thermogrammetric curve indicates the final temperature at which the cumulative weight change reaches its maximum value corresponding to the complete reaction.